not sure which speaker, but probably this one. Yeah, so welcome back after the coffee break. I believe that was the last coffee break today. After the break, Gurgen will talk about decentralized FHE computer. So, yep, please a round of applause for Gurgen, and we'll start.
Hi, thank you. My name is Gurgen. I'm from FHE, and today we have short talk, but I would like to cover the main topic, which is FHE computer we are building at FHE. This is the agenda of my talk. The main topic is FHE computer, but before I will go to details about FHE computers, I would like to cover some short intro about FHE and challenges for FHE developers and component-based approach we're utilizing at FHE, because it was one of the motivation for us to build FHE computer. So FHE, what is FHE? It's just encryption form that allows us to make computation of encrypted data. Powerful thing, and this is what we have right now. And this is what we can do, what we can solve with FHE is just a few examples in blockchain and in AI. And this is things I personally believe that can be solved in general only with FHE. And what about FHE? What about the current landscape? The main thing about FHE is FHE schemes. And the first scheme, fully homomorphic encryption scheme, was developed in 2009 by Craig Gentry. And since that time we have, does it work? Yeah. Since that time, different schemes have been developed. On this slide you can see the most popular ones. And the point here is that there is no some universal scheme. We have different schemes, and you can choose some universal scheme and utilize it for everything. The same about FHE libraries. So there are different libraries here, for sure not the full list, but the most popular ones, OpenFHE, Latigo, and TFHE-RS. It differ in kind of languages for developers, schemes that's supported by library, and the license. And also depends on what you want to build, how you would like to utilize it. It's open question which library you have to choose. Okay, it's just some very short intro about FHE, and I would like to go through from developer's point of view, and let's consider some real use cases. Let's consider privacy preserving computation in machine learning, namely in neural networks. And let's think that we would like to build some privacy preserving neural network. This is some general neural network where we have input layer, we have several internal layer, and we have output. And we would like to evaluate this neural network, proceed the data, which should be encrypted. And the main problem for us, as for developers here, what we would like to do, we would like to encrypt X1, X2, etc., and proceed it in encrypted form. And the main problem for us will be to implement a neuron, which will take as an input encrypted X and proceed encrypted output. And the main problem will be how to evaluate activation function in most cases, because basically all modern FHE schemes by default supports two operations, addition and multiplication. Depends on the scheme, you have some additional operations, but it's also not the same when you work in open data. And the question here for us as for developers, okay, I can do addition, I can do multiplication, maybe I can do some additional operations, but if I would like to evaluate some activation function like ReLU function, how I can do it in this limited basis. And this is the main problem for developers, and the only thing that can help you a lot at this stage is some pre-built components. FHE component you can use. So this is just example of components that can be helpful for you at this stage. So if you have some components that can evaluate ReLU, Signum, logistic regression function, it can be useful for you to build your neural network. And this is the first problem we are focusing on. And we consider all FHE application as applications that consist of some amounts of components, and you just connect these components at some specific logic. But this is one of the core assumptions, that all logic can be implemented as set of components that can be connected to each other. So each application can be considered as the circuit. And we would like to provide the rich set of components. And what we are doing, we build library of these components, which is universal components, which means that it's that depends on the component. You can have different schemes. And this is just the first one of the first our product is Polycircuit library, open source library of FHE components. You can just take it, use, and build your applications. The problem with such library is that to build each component is some state-of-the-art work. And it's quite difficult to build rich set of components inside one team. And this is why to build these components, this library, we utilize approach based on competition. And for it, we developed a challenges platform that on which we can publish different FHE challenges. And participants can participate, solve challenges, provide solutions for some components. We, at the final, can select the winner. At the same time, it's totally fully automated, which means that during the process, during the challenge, you can submit your solution, you can see the result immediately, which accelerates some competition around it. And finally, we can choose the winner, we can choose the solution, and we can publish it as the open source component without any restrictions for developers. So we protect rights, so we don't publish it by ourselves. We publish it with developer name, and we publish it under Apache license, so which means that you can use it for commercial and non-commercial use. At the moment on the platform, you can find challenges developed by IBM. You can find challenges which you can solve with different libraries, at least OpenFHE, Latigo, and the platform library agnostic, which means that we are constantly extending the library and the ecosystem around it. And two types of challenges. In one, in white box, it's needed to upload source code. In black box, it's just enough to upload your ciphertext, final ciphertext, that can be considered as some kind of proof that you have solution. The problem with building FHE components and applications that current FHE libraries compilers require a lot of knowledge in cryptography in FHE. And this is why another thing we are building is FHE toolchain, which built around FHE compiler we are working on, we developed. This is MLIR-based compiler, and MLIR, this is multi-dialect approach to build compilers, which is a great choice to build FHE, because with this approach we can do a lot of things around optimizations and everything related to here. This is about ecosystem around computer hour motivation, and the core of this system is FHE computer. This is basically is decentralized network of heterogeneous computation nodes. We call it fermosectors. Each node can provide source, can provide different opportunity to relate different components, and components is just some basic unit in our ecosystem. Our computer has multi-layer design. At the top layer, we have FHE market, which is the marketplace for application, which means that at this layer, we placed, and any developers can publish any FHE application for private or for public use, which means that you can publish your application. If someone uses your application, you will have some royalty. Orchestration layer, it's one of the core components, because when someone tries to run your application, we have different amounts of different nodes, and we need to somehow to orchestrate computation over computation for application. A little bit later, I will show how it works, but this is important component. Verification layer. we believe in the world where we consider all actors and all consumers as potentially active attackers. And this is why we need strong verification layer, verification protocol. Execution layer is just the set of actors. And data layer for FHE, it's important to have separate data layer to be able to store data ciphertext off-chain, because it's not possible to store it on-chain. And also we have different bridges that allow us to be connected to other blockchains. Marketplace, as I mentioned, is just marketplace of application. Anyone can publish application. About execution. So as I mentioned, when you try to launch application on our computer, as far as it's component-based application, for each application on orchestration layer, we can create some execution graph, which consists of different kind of blocks. It may be component or it may be some bridge. Bridge usually is just some way how we can connect different components. Because basically, when you relate one component and you would like to run another component on the output of the previous one, in most cases you need to do some intermediate work, mostly around repacking. Because in most cases, the format how data is encoded for one component, for the output of one component, is not suitable for another one. And this is why we have separate type of components which called the bridge. When the graph is built on the orchestration layer also, for each component depends on the parallelization approach, we choose the actors who will evaluate certain components. Also, it works as on the real market. We have order book, and depends on the state of the order book, depends on the state of the network, component can be delegated to some actors. To be stable, we utilize multi-layer approach, which means that we can use different layers for backups actors. And as far as we don't have opportunity to manage all actors for all applications, we developed the approach where we are able to choose just pair, or it may be L actors for each components, and each actors in the pair just working together, manage each other, and if main actors fail, they just change, fallback actors will just take the place on the main actor. And we will, at this step, we will find the new fallback actor who will back up new main actor. This is fully dynamic story because also depends on the execution graph, depends on the execution layers. The availability for actors is changed, and we make decision about how to delegate this component or other components just in the time when we need to run it. As I mentioned, important thing in our ecosystem is data layer, and this is IPFS-based data layer we utilize for building our network. And also there are a lot of hard work around it, because when you try to build some execution graph, when you try to make some orchestration, you need somehow to take into account that data can be stored in distributed and decentralized data layer, and you need to find a way how to minimize data transfer, because when you work with FHE, data maybe is too hard and too big. Another interesting thing about our approach is royalty model and fee sharing model with developers. And the idea is that here you can see our ecosystem in general. We have a few main components. So we have FHE market here, and each applications built based on some opcodes in our virtual machine. And each opcodes depends, which means built based on different components. And the idea is that if you are a developer, if you developed some components and you can provide your components, and your components is used inside our ecosystem, so which means that if someone run this application, it means that all developers that contributed to components utilized in building this application will have some royalty. And here, interesting thing is that how we can decide which component should be added to polycircuit. And here, the place where Firma is going to help us with it, because with Firma, we can with Firma build benchmarking platform. And Firma in our whole ecosystem plays the role not only just of FHE challenges platform for fun, it's significant and important layer in our ecosystem, because you as developer, you can come to our ecosystem through Firma platform, you can challenge any component you see, and if your components better than components we have in our polycircuit library, your components will be integrated in library and your components will be used for applications on our app store. And since your component is integrated, used, since that time, you will have royalty. Just some few features about our ecosystem. Scheme and library agnostic. It's important because, as I mentioned, we believe that at this stage we don't have universal FHE scheme, and moreover, we believe that in a few years we will have total new FHE scheme. Fully trustless environment that allow us to be scalable, which means that anyone with laptop or data center, you can be connected as an actor, and it's not needed to provide some verification. We provide support for private actors, and it's also important and interesting thing because it means that you can develop some component. So maybe you developed algorithms that allow us to fast evaluate a ReLU function. And you don't want to provide the source code, but you would like to provide it as the service. You can just be connected to the network and say that, okay, I can evaluate this, I will evaluate, just send me a result, send me a ciphertext, I will do it. Without sharing source code. And this is private actors, and for it we have separate verification protocol. And the last thing is coprocessor for L1, L2 networks, and core logic placed on L1 network. That's all. Thank you. We'll be happy to answer any questions.
Thank you, Gurgen. Unfortunately, we don't have time for questions, so thank you very much for your presentation. Round of applause for Gurgen. And right now, last talk by Damian, I believe. Grzegorz. Oh, sorry. Sorry for that. By Grzegorz, who will talk about Cairo. I believe this is true.
Yes. All right. How do I make this work? Oh, okay. Sorry. All right. Before we start, quick question. How many of you ever interacted with Cairo or StarkNet? Raise of hands. All right. I see one person. How many of you ever interacted with Noir or attended a workshop earlier today with Noir? Anyone? No? One? Okay, great. Cool, we'll make it work. So I'm Greg. I run Ray Labs. It's a research and development company specialized in ZK. And today I'm going to talk to you about making your Cairo programs faster, cheaper to prove. But you can substitute Cairo for pretty much any sort of ZK or provable programming language. You can apply similar techniques to whatever tools you choose to use. So Cairo is a smart contract programming language for StarkNet. StarkNet is L2 rollup like Aztec and many others that were presented today. And Cairo is a very easy way to get started with ZK because it has Rust-inspired syntax. Like I'm going to show you later, the code looks pretty much like if you written regular Rust code with the additional benefit that you can actually prove that the program that you wrote actually behave as you expected. And I'm going to walk you through an example of building a Stark VRF. VRF, or Verifiable Random Function, is a technique that we can use to generate pseudo-random numbers in ZK environments. And what this means is, imagine you're running an online casino, and you as a player, you want to make sure that the casino doesn't cheat on you when the stakes are high, right? So you have some money on the table, and you want to make sure that whatever dice roll you get or anything that happens in the game you're playing, that the casino couldn't just, pick a result and just hand it over to you, but that they actually did it fairly. And then on the other hand, you as a casino, you want to make sure that the players cannot predict results, so that they don't only play when they know that they're going to win. And the way verifiable random functions usually work is that you have two actors. One of them has their own private key that they don't share. That private key is necessary to generate the random value. And then you have another actor, a player, who provides a seed. And then you have to combine those two information, private key and a seed, to be able to obtain a random number. And you as a player, you can verify that the casino or the prover didn't change their private key in the process, so that they couldn't influence the results. Like once you commit to a public key, you can only generate one pseudo number for a specific seed. And this work is based on like an RFC that's public. But the twist that we're trying to do was implement VRF using a Stark curve with the intention of being able to verify these results as quickly as possible on StarkNet, as cheaply as possible. So we took the spec mentioned earlier, and we implemented it using the Stark elliptic curve and Poseidon hash that are cheap to operate on in the context of StarkNet. At least that was the theory. Unfortunately, the first benchmark we ran after implementing the spec, it was like super, super slow, super expensive to run. And actually, I think like with over 300 million gas users, you wouldn't be able to actually run it on StarkNet. And the reason for this was because, as I later realized, within the spec, we're really trying to calculate a square root function, which is famously difficult to do in arithmetic circuits, because you only have essentially addition and multiplication available. So if you want to calculate a square root, you have like this complex code that, in the context of Cairo, operates on 250-bit numbers. So we have a bunch of exponentiation here. Even with fast exponentiation, if you have 250-bit long numbers, it's going to be hundreds of multiplications that you are later going to need to prove. The thing is, we don't really need to do any of that in the context of verifiable or provable programs, because we don't really care how these results were obtained. We don't care about executing a specific algorithm to calculate a square root. The only thing we care about is that the square root is actually a square root. And the only thing we care about is verifying, asserting that the output of square root function multiplied by itself is equal to the original input. And as long as we have that, we are happy. So we don't really care like how these numbers are obtained. And a lot of time in mathematics, or in cryptography, the sort of like black box function that provides you values out of seemingly nowhere is called the oracle. And in our particular case, the oracle can be very, very simple, and it can be as easy as a piece of cold data. So when you run your function to verify that the random number that you got and the proof that you got alongside is correct, you also insert one additional number, which in this case is just this particular value. Like we need to calculate square root runs in the verification process. So if we can provide it ahead of time from the prover, we're golden, and our benchmark is suddenly 150 times faster by just using this, like by providing this one square root value. So this is great, and I see you've mentioned that you don't use Cairo, so it's probably not interesting for you. But if it is, you can grab the code from here. It's open source. It's working. But cold data itself is not that exciting. It's very, if you want to take a picture. The cold data is great, but we can do more. if we don't constrain ourselves to operating on StarkNet, what we can also do is we can look at programs that run on our own machine. We can look at the case of local proving, where we have a bunch of more interesting scenarios available. So the problem with cold data is that, well, first of all, we have to think about all of the cases that are hard to calculate ahead of time. And here we only had one number. But imagine you run an algorithm where you, for example, need to calculate pairings and you need to sort of get hundreds of values. You suddenly need to implement the same algorithm twice. You have to implement it in a language that is going to make these operations fast for you, say Rust, but then you have to do the same thing in Cairo using the values that you got from Rust. So that's a bit annoying. It would be great if you could just do everything in Cairo, write the code once, test the code once. And so what we can do is we can leverage the fact that you can prove Cairo on your local machine. There are a bunch of different provers available. There are actually guys from Herodotus here who wrote integrity verifier that you can run on StarkNet to verify those Cairo proofs on StarkNet. You can also verify those proofs on EVM-compatible blockchains like Ethereum using StarkNet's verifier itself. So that gives you lots of options of sort of running your or verifying your Cairo proofs in ecosystems that are already used by millions of people. And there are many interesting applications of being able to, I call it interactive oracles, like being able to sort of stop your Cairo program, get some inputs from outside the world, and then restart your Cairo program. Giza is one of the companies that were contributors to the Hints projects that I'm going to show you later. They, for example, use it for verifiable AI or machine learning algorithms. So being able to prove that they run a sophisticated model. And when you think about it, ML is like tons of matrix multiplications. It's like people spend tons of money on expensive GPUs to be able to run, you know, many things in parallel as fast as possible. Like, how the hell do we do this in an arithmetic circuit? And the idea here is that you just don't. You do your matrix multiplication outside and you verify just like either one or a few random elements in the circuit to be sort of certain that the correct algorithm run. You can use these sort of like interactive ways of getting data for doing recursive proofs when you need to do wrong field arithmetic. And there is this white paper by Geometry, I think, where they describe how you can make it faster by leveraging hints. And you can imagine that's also a great way of storing private key, assuming Cairo was actually easy, or provers that we have were actually zero knowledge, where you can do certain computations in the trusted environment and then just plug in the numbers using hints. So I don't know if we still have time, but I'd like to give you a brief overview of how this looks in Cairo, should you decide to use Cairo after this talk. The way we allow this interaction between Cairo and other programming languages is through HTTP server that can speak JSON and protocol buffers. So you first define your interface using protocol buffers. You define what are the functions available, what are the functions that are going to be available in Cairo, and then you call our library to generate Cairo code for you. And it's really important, not only in Cairo, but in any sort of arithmetic circuit tool that you decide to use, that whenever you start injecting data from outside, whenever you start relying on some additional inputs from into your programs, you have to be extra sure that you verify that you got correct numbers. Because like suddenly we don't execute code line by line, we have some out of order execution that just plugs some data into our memory. And what Cairo hints cannot do it for you is it cannot verify that the thing you got was correct. So it's really, really important that whenever you use hints, again, whether it's Cairo or something else, that you constrain the values that you get. So in the case of VRF, what we can do is we can have this oracle, we can have this external function that is going to give us a random value alongside with a proof. And then we have to be extra sure that we actually verify the proof. we cannot just say, okay, cool, I got a random number, I'm gonna run with it, I'm gonna, you know, play my casino game or whatever. I have to be sure that I call this verify function to make sure that the randomness was provided correctly. And I cannot stress this enough, you have to constrain your code. Like, whenever you do anything with ZK, you have to be extra sure that you think about all of the constraints that you have in your code. And there's been a ton of high-profile projects that were owned by just having under-constrained circuits, so like not expressing all of the requirements necessary for your program. There is an ongoing risk on 0xPark GitHub with like many high-profile projects being broken because of not constraining their circuits enough. If you actually decided to use Cairo, this is how you run our library for hints. You can get it from here if you're interested. You can learn more on our blog if you're interested. I see, okay. Yeah, I think that's all. Like, any questions?
Right. Thank you, guys. Thank you, Gregory. I don't think we have time for questions. Like, that was today's last talk here, and now there are closing remarks on the main stage. So let's come in, but round of applause for Grzegorz.